All right, so for this lecture, we're going to talk a little bit about the Coulomb Force. We're going to introduce it, but only stick with 1D examples today, and use this as an opportunity to review how to set up and solve Newton's law problems, which necessarily involves us dealing with vectors, but today, we're going to stick with 1D, just so that we can go through the steps systematically, so that when we do multidimensional next time, it's not quite as novel. So, review from last time. Last time we talked about charges, that they come in kind of two flavors, positive and negative, which we now know is a result of the protons and the electrons in atoms. As a result, charge is quantized, and that the net charge is the total charge, is some integer n multiplied by this fundamental charge constant E, which gives you the amount of charge per electron or per proton. It has a unit called a Coulomb, which seems like it might be connected to what we're going to talk about today, indeed. And then we also talked about the mediums that charges can exist within insulators and conductors, that we won't worry too much about today. So, today I want to talk a little bit about density, just introduce or remind us about the concept, and then do some Newton law 1D problems with this Coulomb force. So, before we get to the new stuff, here's one example. A bottle of water, which is half a liter, has how many water molecules? In order to answer this, let's use the density of water as 1 gram per cubic centimeter, or 1 gram per cc. It's going to be 10 cc's, it's cubic centimeters. So, this problem involves necessarily us using this thing called density, which you probably saw last semester, but we can remind ourselves of what this is. So densities are telling you how concentrated a quantity is. And this concentration, so in terms of mass density is telling you how mass is concentrated over some sort of line or area or volume. Densities can either be 1D, 2D, or 3D. 3D is probably what you are most familiar with. We will see kind of all of these in this class. So, to use water as an example, if I say that water has a density of 1 gram per cubic centimeter, what that means is that if I take, if I have a bottle of water and I break it up into a bunch of cubic centimeter little cubes, and to give you a sense of what that is, right, your pinky, from kind of bottom of your fingernail to the tip of your pinky. That you kind of imagine if you were to, well, it's kind of gross, but imagine if you were to cut off the tip of your pinky, right, from the base of your fingernail up. That's a good approximation of the volume of 1 cubic centimeter. So, to say that water has a density of 1 gram per cubic centimeter means that if I randomly picked, a cubic centimeter somewhere in that bottle of water, the amount of water in that little cubic centimeter would have a mass of 1 gram. And cubic centimeter, since this is over a volume, length times length times length, this therefore is a 3D mass density, how mass is distributed over a 3-dimensional volume. So we'll also see things like a 2D density, which might be how something is distributed over an area, how much is something distributed over the surface of an object, say, or a 1D density, how much stuff is distributed over a line. And maybe you saw this last semester if you talked about, say, the density of a string. You can talk about the mass per unit length of a string. That's kind of a 1D density. So what this is telling you, again, a density is connecting mass to volume, in this case, for a 3D mass density. And so that then gives us a relationship that the mass is therefore the density multiplied by the volume. Now, I'm not sure, this is maybe something that's maybe worth remembering, but really all this really is units. A density is a mass per volume, so density times volume, therefore we'll just have units of mass. So there is a connection between these three quantities, mass, density, and volume. which again, just really dimensional analysis. So, going back up to our problem now, I have half a liter of water. How many water molecules is that? Okay, well, first thing we need to know is, what does a liter convert to? So that's just something that you can look up, just a definition. A liter is defined to be 10 to the minus 3 meters cubed, or 10 to the positive 3 cubic centimeters. So another way you might see this is that as 1 milliliter, which is 1,000th of a liter, therefore is 1 cubic centimeter. Saying the same thing. So in this case, if I have half a liter, that's the same thing as half a liter. And I have my unit conversion, where I'm going to put 1 liter on the bottom and 10 to the 3 cubic centimeters on top. The liters cancel. It looks like I get 1/2 times 10 to the 3 cubic centimeters. Or, it's not quite yet in scientific notation, 10 to the 3 is just 10 times 10 to the 2. And I'm dividing by that 2. So then I've kind of yanked out a 10, because then I know 10 divided by 2 is just 5. So then this is the same thing as 5 times 10 to the 2 cubic centimeters. All right, that doesn't quite answer the question yet, but maybe that's useful. All right, why cubic centimeters? Well, I used cubic centimeters because the next step is to use the density. The density can then allow us to turn this into a mass. And the density that we're given already has units that involve a cubic centimeter. So I could then ask, what is the mass? The total mass I have is then going to be density over volume, density times volume. So that looks like then it's 1 gram per cubic centimeter. And then our volume we had was 5 times 10 to the 2 cubic centimeters. Cubic centimeters cancel. And it looks like then I get that this is 5 times 10 to the 2 grams. So that's how much mass of water I have. Now we have to start thinking about how I can convert this to something that is in terms of individual molecules. So I know if I think about H2O, that means it's 2 hydrogen plus an oxygen. So if I knew how much hydrogen and oxygen weighed, or what mass they had rather, then perhaps then I can get maybe a mass per molecule, and then I could use that to convert my 5 times 10 to the 2 grams into a number of molecules. Here's where the periodic table comes in. Always good, probably, to have a periodic table bookmarked, on your browser. So if I look at the entries of the periodic table, the hydrogen and the oxygen entries are probably going to be the ones that play a role. And just to remind us, let's go back up here. Stick up here with the oxygen one. This 8. This 8, of course, is the atomic number. How many protons are in the nucleus? And what we're going to need is the other number that's often shown, which is the atomic mass, or atomic weight. It's sometimes written for the chemists. So this atomic mass is telling us something about not what each individual atom weighs, but again, since chemists are often dealing with, like some sort of some quantity of it, they're never just looking at a single atom or a single molecule. They usually are looking with some solution that has, xads of stuff in it. So they, of course, like to use the mole as a way of quantifying these things. So in this case, I'm not sure why atomic mass is glowing. So what the atomic mass is telling us is atomic mass tells you how many grams per mole of that atom there is. So this tells you that there is 15.999 grams of oxygen per mole of oxygen. So if I were to have 1 mole of oxygen, Avogadro's number, 6.023 times 10 to the 23. If I had 6.023 times 10 to the 23 oxygen atoms, they collectively would weigh or have a mass of 15.999 grams. Similarly, for hydrogen, hydrogen then, 1 mole of hydrogen has a mass of 1.008 grams. So, how does this help us? That means that if oxygen and hydrogen, so hydrogen is 1.008 grams per mole, and then oxygen was 15.999 grams per mole. Then H2O, which would be 2H plus 1 O, and that suggests that it should be essentially 18. But if we add those together, then we get what? It looks like it's 18.015 grams. And again, I'll be very explicit with the units per mole of H2O. So 1 mole of H2O molecules has a mass of 18.015 grams. That then gives us the next conversion factor. So then if I have 5 times 10 to the 2 grams, and then I use this now as my conversion factor, that 18.015 grams of H2O is the same thing as 1 mole of H2O. And why not let's just do the rest of the problem all at once. And then I know that 1 mole of H2O is Avogadro's number of molecules, so 6.023 times 10 to the 23. Again, I'll be super explicit. H2O molecules then the grams cancel, the moles of H2O cancel, and I'm left with number of molecules at the end of the day, which when I plug everything in, I get 1.67 times 10 to the 25 H2O molecules. Which then is our answer. Maybe I'll highlight these. There we go. So in this case, the density, just to look back, the density allowed us as a way of converting between volume and mass. And then the atomic weight or the atomic mass given from the periodic table allowed us to convert between mass and number. So we'll see that again in this course and on problems related to this material. So good reminder of stuff the periodic table can tell us. All right. Let me now define the Coulomb force and its properties. And then we're just going to do, I think I have 3 examples that we'll do, and that'll be it. So the Coulomb force, from Charles Coulomb, who was studying this in the 18th century, he published this work in 1785. He was kind of inspired from the work that Cavendish had done in trying to study the gravitational force. And so in doing this, he came up that he was one of many people that was studying electricity in the late 18th century. And he was able to come up with a quantitative form for the magnitude of a force that is exerted between 2 charges. And the interesting thing about this, just to give a little history, is that it seemed to be one of these weird long-range forces. Forces that can be exerted without 2 things having to touch. The vast majority of forces involve 2 things touching. I push on a box, I kick a ball, That's because there's contact between the two objects, and then the force arises because of that contact. Forces, if I were to define forces in an upper level physics course, forces arise are the result of interactions between two systems. And they often always involve contact. Then gravity, kind of was like, well, actually, this weird thing seems to be going on with gravity where they aren't touching one another. I can drop a ball and it's pulled towards the Earth even though it's not touching the Earth, at least initially. Same thing seems to be going on with these charges. Two charges can exert a force on one another even though they don't seem to be touching one another. This bothered people, this bothered physicists of the time, because they were fairly convinced that forces required this sort of contact. And most of this course, we will introduce this idea of the field. The field is essentially a way of allowing forces to, or two objects to interact without them having to necessarily touch. There's essentially a liaison that is operating in between them, which is called the field. But we're not doing fields yet, we're just dealing with the force quantitatively. So, what Coulomb was able to show is that this Coulomb force, and there's something that's called the electrostatic force, because when charges start moving around, you have to be a little careful. So for most of these initial problems, everything's going to be held stationary, or we're just going to look at a fixed moment in time when things aren't moving around yet. He was able to quantify that the force, and remember, forces are vectors. What does it mean to be a vector? A vector has a magnitude and a direction. So if I'm going to write down a vector quantity, I need to tell you two things. What's the magnitude and what's the direction? Again, we'll review vectors in their kind of formal way next time. But for right now, we can write down the magnitude of the Coulomb force he found to be, remember, these kind of absolute value signs around a vector specifies the magnitude of that vector, or the length of the vector if we want to get technical. That this magnitude was some constant k times the absolute value of the product of the charges. So you have charge 1 and you have charge 2, and I'll just take the absolute values and multiply them together, so don't worry about negative signs or anything. And then I divide by the square of the distance between them. I should have defined that. All right, so this r is the distance between the two charges. Right, the two charges, Q1 and Q2. This K is just a proportionality constant, sometimes called the Coulomb constant. Your book calls it the electrostatic constant. And it just has a number of 8.99 times 10 to the 9. And then this thing has to also make all the units work out. I know this has units of newtons. This has units of coulombs, this has units of coulombs, this has units of meters, and it's going to be meters squared. So, you could use this as an exercise. Convince yourself that K therefore must have a unit of Newton meter squared per Coulomb squared. Because then when you multiply all this together, you ultimately get a unit of newtons. So that's just a number, K is just a number. The charges, if you have two charges that you're studying, what are their charges? Plug those in there. And then r is then the distance between them. Just don't forget to square it. That's the magnitude. The direction is our familiar, we're familiar with like charges repel and opposite charges attract. That's where this comes in. That's the direction here. If Q1 and Q2 have the same sign, which means they're both positive or they're both negative, then they're going to repel. If they have a different sign, which means one's positive and one's negative, then they attract. So this is just saying opposites attract and like signs repel. And this is dealing with kind of 2-point particles. So if I have 2-point particles and I'm studying the force between them, then this force is the appropriate way of calculating them. In reality, of course, things aren't really point particles, but this is often, as you did last semester, a great approximation for many things. So a couple quick things, just conceptually. this probably looks very familiar. This is very, very similar to the way that Newtonian gravity works, where it was g m1 m2 over r squared. So it's one of these inverse square law forces, or what's called an inverse square law. Again, just meaning that it depends on the inverse square of the distance. Inverse meaning it's 1 over r. It's not r squared, but it's 1 over r. And then it's a square law. There's a square there. Just like gravity. But what makes this a little bit more interesting is that with gravity, you can only have attraction. Two masses only attract one another. But for the Coulomb force, you can have both attraction and repulsion. So, and then last but not least, we'll see this in the upcoming sections, but I want to write it down now. This constant k is often written in another way, where this k can be written as, instead 1 over 4 pi, a new constant times epsilon naught. Well, this arises in the way that we define some, stuff called the electric field. So, when we get into fields in the next section, this epsilon naught, which is called the permeativity constant, is essentially saying how the electric field can permeate through space. And again, don't worry too much about this right now, but I'm just putting it there for completeness. So sometimes you'll see F is 1 over 4 pi epsilon naught times Q1, Q2 over r squared. But I, like your book, think it's kind of just nice. Let's just lump this all together as a single constant rather than dealing with 4s and pi's and all that such. So we'll just keep it as k. But this epsilon naught, again, you could easily work out. If I know k, I know 4, I know pi. That implies epsilon naught is 8.85 times 10 to the minus 12 Coulomb squared per Newton meter squared. And again, thinking about the directionality of these things, if I have two charges, Q1 and Q2, then the direction of this force, we can talk about whether they attract and repel. The direction is always along the line connecting the two. So if I have the two forces here and I draw a dotted line connecting them, then that tells me that the force must be somewhere along that line. So if it's repelling, it's here. If it's attracting, it's here. Similarly, if it's attracting or if it's repelling, the forces are always along that line that connects the two. It's a center-seeking force, sometimes these are called. But I don't think that should be too surprising here. So I say this because we will see that the magnetic force actually does not have this property. The magnetic force will operate kind of perpendicular to this line. Okay, so we've seen this before in the sense of we've seen, how a gravitational force, an inverse square gravitational force law operates. So conceptually, a lot of that can track over. So I think for today, again, let's just do some simple 1D problems using this force, just to remind ourselves of how to set these problems up. And so, since it's probably likely that you were not taught the same way I would teach it, I essentially break a Newton's law problem down into 6 steps. And we'll go through, explicitly doing these steps in the next couple examples. The examples are going to be pretty simple, again, so that I can emphasize what's on your screen here. So let me just go through them, just read them real quick, and then again, we'll kind of do them step by step in the next examples. So if I'm solving a Newton's law problem, the first thing to do is identify my system. What am I solving for? Am I solving for the box that's going down the inclined plane? Then the box is my system. Maybe a box is rolling down an incline or sliding down an incline, but the incline is also on a sheet of ice, so the incline could also move. Then maybe I want my system to be the incline, and I want to study its motion. Or in this case, it's going to be I'm going to have 2 charges, and I'm going to study the resulting motion of one charge from the other charge. So I have to identify my system. What am I studying? And then once I identify my system, I can then identify all the forces that are, all the objects that are touching the object. Anything that touches the object must therefore exert a force. Forces arise because of interactions, so anything that's touching my system must exert a force on that system. My cat has woken up. Next thing to do is, besides all the forces that are touching the system, you then have to pause and make sure that you might also consider all the possible long-range forces. First semester physics, there was only one. It was gravity. The Earth did not need to be touching the object for a gravitational force to exist. Here, now we've introduced another one, this electrostatic force. If I have charges do not need to be touching in order for this long-range force, which quantitatively is given by this, to exist on the object. So this is essentially identifying all the forces acting on the system. At that point, you can write out Newton's second law. The sum of the forces is the mass of the system times the acceleration of the system. Note though, however, in this point, I've never said anything about minus signs, whether, or anything like that, because to me, that comes in step 5, where you establish a coordinate system in order to get the force components. If I want to write the force of gravity as mg, or maybe it's negative mg, well, that depends on my coordinate system. That depends on what I define as up and down, and which direction I define to be the positive direction. There's no reason why I can't make the negative direction be up. You're free to always establish a coordinate system to be whatever you want. And only then can you write down forces in terms of their components. And then you solve. So let's go through these steps with some simple examples. So here's a problem. I have two charges. I have a charge over here that has a charge of plus 2e, and it turns out that it's 2 protons. Then I have another charge over here that has a charge of negative e, and it turns out that it is a single electron. And they are separated by 6 millimeters. And the question is, what is the force and the acceleration of each of these point charges? So for each of these quantities, I want to calculate a force, which means a magnitude and a direction, and an acceleration. And remembering from first semester physics, that's also a vector, so I need to also say something about a magnitude and a direction. All right. I'm going to need a couple copies of this. So let's see here. So let's do that. And I'll copy another one, because I know I will need it eventually. Okay, so step 1, identify your system. So how about we stick with this one first? So, yes, thank you for your contributions. You have food here. Sorry about that. It's probably not going to be the last of him. So I'm going to define this as my system. Step 1. That's the thing I'm going to study. And then maybe I'll even write it out explicitly here. 1. So system is identified. 2. Is there anything touching my system? Because if there's something touching that system, then that exerts a force on my system. If it were a box on a ramp, the box is touching the ramp, so there better be a force from the ramp. You often would call it the normal force, or it would be normal and a friction force. In this case, there's nothing touching. Oh, so no forces. So then, what about long-range forces? Well, in this case, there is a long-range force that's going to result from this charge over here, which will make it a different color. So, if I want to draw an arrow to represent that force, these are two opposite charges. One is positive, one is negative. So I know that this force is going to be pointing, or it's going to be an attractive force, so I know that that arrow is going to be pointing towards the right. So that is our long-range force. And here I'm going to be very, very explicit about how to how to write down this force, which is, it might seem like overkill, but it really helps in the long run. So this is going to be a force, which is a vector. I'm going to write this is going to be the force on Q1 from Q2. That's all kind of just a massive subscript. The force on Q1 from Q2. Or sometimes I will write it just as kind of force Q1 slash Q2. Where it's on Q1 from Q2 is what I mean by that slash. And the point of this is to identify, we're identifying things that operate on our system. Our system right here is Q1, right? So the force on Q1. But that force must always come from something. And it can't come from itself, right? A system can't act on itself. So I need to identify what other object, what other system is exerting this force. So that's why we have on Q1 from Q2. Again, probably seems like overkill because there's only one force, but we'll see this will be helpful in the long run. All right, so then at this point I can write down Newton's second law. So Newton's second law says that the sum of the forces on Q1, because that's my system, equals the mass of Q1 multiplied by the acceleration of Q1. That is what Newton's second law says. I've said nothing about negative signs or anything like that, but it says the sum of the forces, that's a bunch of pluses, equals the mass of the system times the acceleration of the system. So in this case, it is F of Q on Q1 from Q2 equals mass of Q1 times the acceleration of Q1. That is Newton's second law. And I know, just by looking at the diagram, I anticipate that this force will be pointing towards the right, and the acceleration will be pointing towards the right as a result. Only now can I establish my coordinate system, where I will actually say which direction is positive and which direction is negative. You are free to make it whatever you want. So if this were 2D, right, you would probably do the usual, where you would say to the right is positive and up is positive. That's typically what's done. But again, you don't necessarily have to do it that way. But once you make a choice, stick with it. So this is saying to the right, and particularly since this is just a 1D problem, right is positive. And then also up is positive. Even though these are 1D problems, I think I will write them as 2D problems just to, again, start to jog our memory about vectors. So at this point, then, I can ask myself, what does f of on Q1 from Q2 look like? Well, it's a vector, and I like to use the brackets for vectors. I know some people like the columns to do it. I kind of like brackets. So then I have to specify, if this were 2D, I have to specify an x coordinate and a y coordinate of what this force is doing. Well, again, there's nothing really going on in the y direction, so it's 0, because this is really just a 1D problem. And then I know that this magnitude better be k, q1, q2 in absolute value, divided by this distance squared. Did I give it a symbol? I did not. So let's go back up here. Let's call this d. Because as you see, I will much prefer to always be working in symbols first, and I would plug in numbers at the very, very end. So at that point, I know its magnitude is k, q1, q2 in absolute value over d squared, and I know it's going to be pointing, based on our diagram up here, to the right. We defined the right as positive, so I'm therefore going to write a plus sign in front of this. It points to the right and has that particular magnitude. And if I want to plug in, I know that it's k, and q1 is 2 times e, and then q2 is negative e, but in absolute value, so it's just e, so then that becomes e squared over d squared, comma 0, and it's plus. So it points to the right with that particular magnitude. Not ready for you yet. Now we can finally plug things in. So then that suggests that Newton's second law says F Q1 on Q2 equals the mass of Q1, it's the acceleration of Q1. And so therefore, it looks like I have K, or 2K times E squared, all over d squared equals the mass, which we said was 2 protons. So I'll write that as 2 times mp for a proton mass times the acceleration. Particularly, this is the acceleration in the x direction. So if I think of aq1 as ax comma ay, really what this is showing me is that if I just look at the x components, this is equal to the mass times the x component of the acceleration. And then of course ay is 0, because ay is going to be 0 equals 2mp times ay. So then it looks like this is saying that a sub x is, looks like the 2's cancel, k e squared over mp times d squared. And I'll make the plus explicit, right? Also to the right. So then we can plug in numbers, right? The force on Q1 from Q2. I plug in numbers, right? I know K. I can look up E, and in D squared, I get 1.23 times 10 to the negative 23 newtons. And then I could plug things in for the acceleration. I do need to look up the mass of the proton. Mass of the proton, 1.67 times 10 to the negative 27 kilograms. Which you might think this force seems absurdly small, 10 to the minus 23. But then we're only dealing with protons here, so when we divide by this proton mass, we're dividing by something that's 10 to the minus 27. That ultimately wins out. This acceleration at the end of the day is 7.68 times 10 to the 3 meters per second squared. Or, looks like it's 7.68 kilometers per second squared. Now, really what I should be saying here is I wrote them as positive numbers, and since I know that to the right is positive, that really is saying that these are values that point to the right. I don't think it really hurts if you also make that explicit, right? So then I can write to the right in this case, for both the force and the acceleration. So then we have the force is this. I'll use a different color. The acceleration is this. Both of them to the right. Okay. Now, what about the other problem? Now, what's going on with the other charge? Well, I won't write everything out in detail as I did before, but first things first, that's going to be my system. That's important. Because now I have to ask myself, is anything touching that system? No. Is there a long-range force acting on that system? Yes. And I expect it to be pointing in this direction as a result, because that's an attractive force. So then I should expect that, since it's the only force in town, that the force on, now here we have to be careful, on Q2 from Q1, notice it's flipped, force Q2 slash Q1, that equals the mass of Q2 times the acceleration of Q2. Now, if you're scratching your head thinking Newton's third law, I like how you think. But we could also be very explicit about this too. So if again, now this is step, step 4. We've written out Newton's second law, is what you see on the page. Now, again, I can establish what direction is positive and which direction is negative, and I'll use the same directions as before, where up is positive, and to the right is positive. which means I anticipate that this particular force that's drawn, since it points to the left, will be negative. And so then force of on Q2 from Q1 looks like it's going to be negative K. That's 2E times E, so it's E squared over T squared. Nothing going on in the Y direction. And again, I would have figured that out by the same formula, right? It's the same K, it's the same Q1, same Q2, same D, I squared. But since I drew this arrow pointing to the left, and that's the negative direction, that's why I put the negative sign in. Now, where Newton's third law comes in, just to remind ourselves of Newton's third law, Newton's third law, if you write it out with my absurd subscripts, Newton's third law, this will be an aside, Newton's third law just says that the force on, say, system 1 from system 2 is equal to negative the force on system 2 from system 1. And it seems like that's exactly what we saw here. And let's see where. And I feel like the subscripts make it really easy to identify this. Okay, so up here we wrote force of Q1 on Q2 and wrote this. And then at this point, I ended up writing force on Q2 from Q1. And I could have immediately identified without knowing anything else that that must be the negative of this, which is what Newton's third law is saying. Between individual systems, that's where Newton's third law appears. So, how does this change the calculations? Seems like then the force on Q2 from Q1 is the same exact thing, but with a negative sign. So this was going to be then 1.28 times 10 to the negative 23 newtons. This negative sign, right, it's just saying, right, it's to the left. But now we have to be careful. The acceleration is not the same in the opposite direction. Newton's third law doesn't say anything about accelerations. Newton's second law says that the acceleration, or rather, the force on Q2 from Q1, since that's the only force, is equal to the mass of Q2 times the acceleration of Q2. So since the force has now a new negative sign, but then the masses are not the same either. So I need, run out of room, the mass of the electron, which is about 2,000 times smaller than the proton, 9.11 times 10 to the minus 31 kilograms. Pretty small. That's not zero. So I can't just plug in zero. So then in this case, looks like then the acceleration is going to be the force on Q2 from Q1 divided by the mass, which in this case is just the mass of a single electron. And at the end of the day, I get that the acceleration of Q2, acceleration of this electron, is negative 1.41 times 10 to the 7 meters per second squared. Much, much larger acceleration, unsurprisingly, because it has a much, much smaller mass. But the forces were identical. Let me highlight again. So let's see, before I made force blue, nope, force blue and acceleration red. So if I can compare these two, the force on the two protons and the force on the one electron were equal and opposite, Newton's third law. They both felt the same force, but they both have a different resulting acceleration because they have different masses. Again, physics 1 example I always like to give. If I kind of just let gravity, let my foot drop, if I kick something, if I kick a tennis ball, the tennis ball goes flying. If I do the same exact kick to a bowling ball, I probably am screaming, ouch. and the bowling ball isn't going anywhere. I'm exerting roughly the same force on both objects, but they have very different resulting accelerations. All right, let's see here. Yeah, so good conceptual things to keep in mind. When are the forces identical? In this case, the forces were the same, just but in the opposite direction, even though one had a charge of 2e, or one had a charge of just e, negative e technically, but just 1e versus 2e. Yet the forces were the same. And again, similar to how gravity operates, the force between the sun and the earth pulls on the earth also pulls on the sun, with equal and opposite magnitudes, or equal magnitudes, opposite directions. But since the earth is so much less massive than the sun, the earth is the thing that does all the moving compared to the sun. So the sun does wobble a little bit. Similar here, same forces, but the protons don't accelerate nearly as much compared to the electron. Okay. Now let's add a third charge. Suppose now I have my Q1, 2e, my Q2, negative e, and then I want to put a third charge that has a charge plus e. And now I'm going to have them be separated by 2 meters, just to make the numbers simple. And I could ask the question, at what value of x, if any, or I'm going to define x as kind of the distance from the left charge to this third charge, at what value of x, if any, can the force on Q sub Q3 be equal to 0? Is there a static configuration in this case? And if so, what's the value of x? You might pause and think about it before we go through it. So is there a location here where I can imagine that if I were to place the charge there, it would feel no net force as a result? Well, first thing to do is start, again, systematically. My system is Q3. So first things first, I want to identify, is there anything touching? No. Then I have to look at long-range forces. So let me color code these things. So if I color code the 2 charges like that, Q1 on Q3, or on Q3 from Q1, they both have the same sign, so they should repel one another. So I expect that this charge is going to be pushed that way as a result. Now for Q2 and Q3, they have opposite signs, so I expect them to be attracted to one another. So for my system, I expect it to be pulled in that direction. So I might not necessarily know what the vector lengths are, right? How long do I make these arrows? That's the magnitude. But I now have been able to state the direction of these 2 vectors. And they're both pointing towards the right. So since both point in the same direction, I'm going to be very hard pressed to somehow figure out a way to add them together and yet have them add up to 0, unless they both happen to be 0, which we know is not the case. So there is no x kind of between the charges. Where the sum of the forces is going to equal 0. And again, on Q3, which is my system. So, again, that's more of a conceptual question. Now it's actually true one that's going to be a little bit more quantitative. So same exact problem, except note here I made this a positive e. So we have positive 2e, positive e, and positive e. Well, again, identifying my system, studying this thing. Then I need to identify if this charge is acting on my system. They're the same charge, so it's going to be pointing going to be repelling. I expect it to be pointing that way. This charge, also the same, also positive. So I expect them to be repelling. So I expect it to be going that way. Now, at least as I've drawn it, it seems possible. That actually doesn't guarantee that this is going to be possible, but at least appears possible. The math will tell us if it is truly possible. And we can try to see if we could reason out conceptually or qualitatively what we might expect. I should have made a copy before I drew all over it. Oh well. Let's make a copy of this. And then erase some stuff. So we could ask ourselves, could I imagine this being true anywhere? Or maybe this is kind of down the middle, that's 1 meter. Could I imagine putting the thing, say, over here? Well, in that case, it's closer to the big charge. And I know that this force depends on the charges themselves, Q1, Q2, Q3, or in this case, Q1 and Q3. And then I'm dividing by the distance between them. And if I move it closer to the big charge, this distance has become much smaller, which is only going to make this force even bigger. So then in the opposite case, I made the charge farther away from Q2, which is going to necessarily make that force weaker. So it seems like I might be overpowered here, where I'm making kind of this blue arrow much bigger, and I'm shrinking this green arrow so that it's probably going to become very hard for me to have them be equal and opposite. Now if I go back and think about what's going on over here, well, I've made it closer to this charge, so I've made this arrow longer. And I've made it farther away from Q1, which is going to make that arrow shorter. Oh dear. But that also had a bigger numerator to begin with. So perhaps the bigger numerator is what will save us, so that even though I'm making it farther away, the numerator will allow these to eventually be equal and opposite. So my hypothesis is that this location does exist, and it's going to be larger than a meter if I measure from the blue charge. Again, where if I'm kind of measuring this distance here as x. So let's see if that's the case. How much room do I have? Okay, I'm going to erase all this. But I'm going to put this here. This is going to be Q3. All right, so once more. Oops. This is my system. Is anything touching the system? No. What about long-range forces? I've lost my chart over here. What about long-range forces? Well, again, I expect there to be a repulsion from Q1. I expect there to be a repulsion from Q2. So the forces on my system, I expect to be kind of F on Q3 from Q1. And then I also expect there to be another force on Q3 from Q2. And those are the only two forces in town, and so that better than equal the mass of Q3 times the acceleration of Q3. All right. I've combined a couple of those steps of anything touching, no. Long-range forces, yes. Write down Newton's second law. Again, notice all pluses because I'm just writing things down as vectors. Now I can actually establish which direction I want to be positive, which direction I want to be negative. So let's stick with the usuals. I'll call up positive and right positive. That then allows me to write down actual components for these forces. And here's where we have to make sure we're careful with our coordinates. So if this distance is x, then this distance is d minus x. Since the separation between the two charges, q1 and q2, is d. Why is that important? Because again, Coulomb's law depends on the distance between them. So then it looks like the force, I'll do on q3 from q1. On q3 from q1, looks like it's pointing to the right. And it is going to be k times 2e times e all over, now we have to be careful, x squared, because it's the distance between q1 and q3. And there's no y component. Then the force on q3 from q2 is pointing to the left. Looks like it's k q2 q3 over, what's the distance between them? D minus x all squared. No y component. So at the end of the day, the sum of the forces looks like it is 2k e squared over x squared minus k e squared over d minus x squared. And that is equal to the mass of q3 times the acceleration of q3. Which technically, since I should write these out explicitly, the x component really of q3. But again, this is a 1D problem, so I didn't really need all this vector fanciness. Okay. Now what are we trying to do again? Or the goal was, is there a location where the force is equal to 0? The net force is equal to 0. So really I didn't even need to write equals ma, because really what this is this is F net on Q3, which of course is then equal to mQ3 times A. Now, if the net force is 0, if the force on Q3 is 0, then that implies what? That implies a 2k e squared over x squared minus k e squared over d minus x squared equals 0. And now we just have to do some algebra. Actually, I can just make a new page because I can't do it in this margin. Let's see. So let me copy this last line. Okay, so picking up. If the net force is 0, then this expression is equal to 0. That implies that, try to see if you can fill in the steps along the way. If I skip over steps, the 2k e squared equals k e squared over d minus x squared. That implies, I see things on both sides. I'm going to cancel them out. Divide by that k, divide by that e squared. So it looks like then it's 2x squared equals 1 over d minus x squared. Then, why deal with fractions when you don't have to? Let's cross multiply. 2 d minus x squared equals x squared. Now again, the goal is I'm solving for x. I'm seeing x squareds, which might suggest a quadratic formula. But the way I've written it, why not just take the square root of both sides? So then this becomes the square root of 2 times d minus x equals x. Just taking the square root of both sides. And this becomes square root of 2 times d minus square root of 2 times x equals x. Then I'm going to lump those x's together. So square root of 2 times d equals, and it looks like this becomes 1 plus square root of 2 times x. And looks like finally, at the end of the day, I get that x is equal to square root of 2 over 1 plus square root of 2 times d. Now notice how I did all of this without putting in a single number. Plug in numbers at the very, very end. If I were to plug in that value for e up here, right? It ultimately, who cares? Because they just canceled out. But the chance I would have made a mistake increases exponentially. If I start plugging in numbers too early. Work in symbols all the way through. Notice, I never plugged in a single number with any of this, except I guess 0. Zeros and ones are okay. And then eventually I was able to simplify all the way down to my answer, which is this. Then I can plug in numbers, of course. I can look up, I said d was 2 meters. This ends up becoming 0.59 times d. And since d was 2 meters, this is 1.17 meters. Now, what about my hypothesis? Indeed, it does look like it was a little bit past halfway. In this case, it looks like it was 59%, to past the first charge, or a little bit past halfway at 1.17 meters. So, seems like we're onto something. So again, the focus here is mostly of how I set things up and being very, very explicit about things. And then once you get to your point where you're plugging in numbers, you just have to make sure you're using the model correctly. In this case, the model being the Coulomb force that you evaluate the magnitude based on this formula, and then the direction based on whether things are repelling or attracting. So that's what we did for all of these problems. So you can look over that in your notes and kind of, again, focus on the setup, I think, this time around. Because on the next lecture, we're going to allow the problem to be two-dimensional, in which case then we also have to worry about, say, breaking a force up into maybe components, which will involve some trig functions. All right, very good.